Hey, welcome back, everyone. This is Dr. Gross. Today's session, we'll look at the paired samples t-test. And in earlier videos, we looked at tests like the ANOVA or the independent samples t-test. And today we'll look at the paired samples, which looks at comparisons within the same group using two keyword related measurements. And so, is there a difference between two related measurements? That's what the paired samples t-test is addressing. And what might that look like? Those measurements could be before and after scores. We'll look at weight before and after a intervention or treatment program. Or two conditions measured on the same participant. So mood in the morning versus the evening. And there would be a significant difference for me. I'm not a morning person. And so the purpose is to focus on the mean difference between two measurements. To answer the question for today's purpose, did the participant's weight change significantly after the treatment or after the intervention? I suppose I called it a second ago. So in today's video, we'll use the data set we've been working with, and we'll add a new variable, post-treatment weight. We'll start discussing the assumptions for the paired samples test. We'll walk you through how to set it up and run it, and then how to interpret the results. So as always, let's do a quick refresher. You have SPSS hopefully opened on your device. And you have two main views, your data view, which I'm in, spreadsheet-like page, and your variable view. In variable view, each row represents a variable that is input, and each column represents a parameter of that variable. Data view is the spreadsheet-like Excel kind of looking format where each row represents a participant or a case, and each column represents a variable. And I suppose it would make more sense if we had something to look at. So I'm going to open up the the last data set that we used in our multiple regression video. And so here you can see in data view my participant data, all 32 participants, and all of the variables that we have entered thus far. My favorite button, the value labels, will switch between our codes and our descriptors. I like to keep the value labels on. Gives me a better representation or idea of the data. And so let's side by side this again. I think that works out well. At least I hope you've enjoyed that change in the last couple of videos. So data view, where we're actually entering the data, and then variable view, where we are manipulating our variable parameters. I mentioned variable parameters. That might have been terminology that was confusing. By parameter, I meant the name, the type, which is by default numeric, and most of the time you want to keep it that way. The width and the decimals, we don't mess around too much with those. However, we have added labels. Values is where we code. And then our last important one, the measure, which describes the scale of measurement. And this is important because it lets SPSS know how to treat this data during these different tests that we do. So in this current data set, we have weight already. We also have height and age, right? And even exercise levels and diet type. However, we haven't added post-treatment weight, and we want to have two related measurements for this paired samples. So we'd like a post-treatment weight, so we can relate it to this variable. So let's go ahead and input our new variable. And we would move over to variable view. And now that we're already in variable view, I'm just going to go to my next available row. And we will add our new variable name, post underscore treatment underscore weight. And by default, it will be numeric. So I'm just going to select tab, and it will by default generate numeric, width of 8, decimal places at 2. I suppose I'll keep it at 1 since the rest are as well. For the label, we can say post-treatment weight in pounds. And lastly, our measure. This is important. We need to set it to scale as it is a continuous variable. And so next we'll go back to data view and we'll locate that new column, our post-treatment weight right here. And we'll begin entering the data. And this is the best way I could do it. Here are participants 1 through 15 and participants 16 through 32 and the post-treatment weight. So go ahead and pause the video if you need to right here to enter this new variable data into SPSS. Get over there. Okay. So we have entered this data now, and we'll go ahead and save it. I already have. And first, before we run the analysis, we need to check some assumptions as we have in the past. And so for our paired samples, our first assumption is the assumption of paired observations. And that is assuming that each participant has a related measurement. The participant one's weight is participants one's post-treatment weight as well. So those are all from participant one. Those are paired observations, and we entered that data, so we know that those were paired appropriately. And that assumption is satisfied since each participant has related paired data that we entered. The continuous dependent variable assumption needs to be met, and that is met because we're using a continuous data. Weight is continuous. So as long as the scale or the measurement is set to scale in SPSS for weight, which it is here, and weight in pounds it is. So as long as that's correct in variable view, then we have satisfied that assumption. Finally, normality. The pair differences should follow a normal distribution. So how do we check that? So we'll go to Analyze, Descriptive, Explore, and then we'll add both of those variables, weight and post-treatment weight, to the dependent list. And then we will check normality plots of tests and histogram under the plots option. And then we'll interpret those tests of normality table. No. Okay, so we'll go to Analyze, Descriptives, explore. I'm going to move both variables weight to the dependent list. Remember, I can also drag that over. In statistics, we can check for outliers by clicking that. That's automatically selected for you, though. For plots, we want a histogram and normality plots with tests selected. So we'll hit continue. And then we will click OK. And let's take a look at our output. And so if I scroll down to my tests of normality, I can see that the significance of the Shapiro-Wilk, which is usually the first one that I will look at, it is significant. It is less than 0.05. So that would indicate a violation of normality. However, if we go over here and look at the other test of normality, it's tough for me to say, it is not less than 0.05. So we didn't violate the normality assumption for this test of normality. So even though there is a slight deviation from normality here, given the robustness of a paired samples t-test and the fact that we have a significant sample size of over 30, we can then look at our normal QQ plot, and if it approximates that diagonal straight line, then we can further assume normality. So again, looking at that PP plot and the QQ plot, we are approximating normality. So we can say that the normality assumptions is sufficient. We could also go into our box plot and determine if there are any outliers. And if there are no outliers, again, we can satisfy the normality assumption. And so does this data set violate the assumption? Again, for small deviations from normality, as we see here in this data set, and given the robustness of the test, it can handle minor violations, especially with a large sample size. And then based off I'm going to give it a shot, Kolmogorov-Smirnov results. I feel like I said Smirnov well. We can again conclude that the normality assumption is sufficient. So next we will run the test. So we'll go to Analyze, Compare Means, Paired Samples t-test. And when your Paired Samples t-test dialog box opens, we're going to move weight into variable 1 box, which I have already. And then the post-treatment weight, or as I have it, weight following intervention, into variable 2. And then I'm going to click OK to run the test. And so what am I looking for in this output right here that was just generated? We'll look into the paired samples statistics table, and we'll look into the paired samples correlation table, the paired samples test table, and you can see those key metrics and what you're looking for as I'm scrolling. In the paired samples test table, that's where you'll see your T and your P values. And so now let's actually interpret these results now that you see what we'll look at and what you're looking for. So in the paired samples statistics, and you can see that here, or you can see it here on screen, the mean weight is 137.5, right, pre-treatment. And the post-treatment weight is 136.167, suggesting a slight reduction. Not much, but a little bit. The sample size is 30. At least 30 were included in the analysis because we had two participants with some missing data. And the standard deviation is around 31 pounds in both instances. And that indicates very similar variability in both measurements, which will produce some interesting results. And I'll explain why. So in the paired samples correlation, I'm right here in the output, and it's also right here. The correlation is 1. It is a perfect linear relationship between the two variables, and that is due in part to the low variability between the two groups. The significance, your two-sided significance, is less than 0.05. It's less than 0.001, so very significant. And the takeaway here is that perfect correlation suggests that it's very, very strongly related. Those are very rare, and we'll talk about why they're rare at the end of the lesson. Next, we'll look at the paired samples test box right here. And again, I'm looking here, but the same data here. All right, the mean difference is 1.33, and that's the average reduction, right, among participants. Participants on average lost 1.33 pounds after the intervention or post-intervention. The standard error of the mean at 0.0875. The confidence intervals, which again can tell us a little bit about the significance of the model. And you'll notice that the lower and upper bound confidence intervals don't contain 0. So in that case, it gives us more confidence to accept the result that the model is significant. We would compare this t value to a critical t value in a t table or a critical t table. You have one on your Canvas account, and this is t value is way above the critical level. So again, the level of significance is less than 0.001, so very significant. Takeaway from that would be that the t-test confirms that the weight after treatment is statistically significant and unlikely due to chance. So lastly, we'll look at this paired samples effect size, which is also incredibly interesting. Cohen's d of 2.781, which is very large. That's a very large effect size. Typically 0.8 is considered the threshold for a large effect size. So a Cohen's d of 2 you wouldn't see very often. And we'll discuss why that is at the end. However, what you would say about that is that the weight reduction intervention was significantly related to the reduction in weight. So the treatment was very, very meaningful, had a significant impact on the participant's weight. So in summary of the test, we would say that it was a statistically significant model. I would cite the p-value with a mean difference. I would cite that. And the effect size, I would cite that. If I were to write this up, my results section might look something like this. And I won't read it all to you, but if you'd like to pause and read, you can. If I were to discuss it, it's a short one, but I might say something like this. And so today we looked at the paired samples t-test and SPSS and looked at its purpose when we would use a paired samples t-test. We added a new variable and checked the assumptions of that new variable. We ran the t-test and looked at the output and interpreted the results. And lastly, I'd like to just make mention real quick of these effect sizes and correlations. It is rare that something would be perfectly correlated at 1 or -1 with anything, really. And likewise, an effect size of 2 is extremely large, and you would not see that very often. So I would like to explain that. It is very rare, and there are only a couple of contexts where a massive effect size like that might appear, or perfect correlation might appear. Although they're rare, it could happen in maybe a controlled laboratory experiment where extraneous variables are able to be completely eliminated. And for example, you might have a cognitive psychology experiment where you're looking at the differences in highly distinct conditions. So, like catching accuracy in a well lit versus a completely dark environment, and they're aiming it straight at you. Imagine that. That would be fun. In perhaps physics, where you're looking at the relationship between force and acceleration. In that case, yes, you would expect that type of correlation and effect size. Or if Dr. Gross is manipulating the data, you could have a similar correlation and effect size. So, but I would not expect that. So, however, a paired samples t-test is commonly used in many disciplines, and a great tool to see if something has worked pre and post test, or pre and post intervention. So thank you for tuning in, and please tune in next time as we discuss SPSS with great ease. Thanks for watching.